as far as why or how limits are useful. Why limits again? Calculus is a limits machine, but why? What are the two big problems of calculus? At least to the foundation of calculus and where it came from. Tangent line problem. How do you get the equation of a line that only has one point? Approach, of course. And then the area problem. How do you get an area of, something with a curved boundary that's not a geometric shape? By approaching, of course. For the tangent line, having secant lines approach the tangent line, and then for area problem, have the number of rectangles approach infinity, or we could say the bases of the rectangle approach 0. But either way, the key word to both of them is approach, and approach leads to limits, and limits will somehow forms the entire foundation, the entire basis to calculus. So therefore, we should probably figure out what a limit is. Here we go. Introduction to limits, which is actually, I think, part of the chapter title. No. Chapter 12's title is Limits and an Introduction to Calculus. Anyway. Whoa. Introduction to the limits, then. I know, right? And you don't know until chapter 12 as to why. You're like, wait, our pre-cal is limited? Man, she got a bad book. That stinks. It's pre-calculus with limits. Yeah, right? Light bulbs all over the room. Woo! It means our book is bigger, longer, more extensive than other books. We have limits. I bet I could totally make a life lesson out of that, but that would be hard. But there is one. It would be too hard. Here we go. Intro to limits. Informal definition. Informal. There's this thing called an epsilon delta definition that college professors would really want you to know. And if you're curious as to the deeper things of math and proofs and all that sort of stuff, you can go looking for literally the epsilon, the Greek letter epsilon, delta, the Greek letter delta, definition of a limit. But for right now, the informal one says, if f of x becomes arbitrarily close to a single number L as x approaches a from either side, the limit of f of x as x approaches a is L. Question, what kind of values, from reading that paragraph, I know you're like, from reading that paragraph, just what kind of values are f of x and L? It's hard for you to know that one, but it should be easier for you to know that one. What kind of values are these? Y values. F of x and L are y values. Because if f of x, we know f of x is a y value, the function values. Way back to the, do I still have it? This worksheet from the beginning of the year. Remember him? The parabola, completing the square, trying to find the max of, that face, the max of, min of, at certain. Remember the of and the at? The max value of, the min value of function, they were y's. At, those were whens, those were locators, those were x's. So when I say f of x value, I'm talking about y values, and if f of x is getting closer, what? Is that what arbitrarily close means? So close, it's basically there? Hey, wait a minute, so close, it's basically there. What have I talked about this year about so close, I'm basically there? Zeno's paradox, right? Cover half the distance. 1/2 plus. Cover half the distance. 1/2 plus a fourth. Cover half that distance. 1/2 plus a fourth plus an eighth. Cover half that distance. Oh, my feet aren't even able to, right? No. Numerically speaking, 1/2 plus 1/4 plus 1/8, there's still a lot of space left. I mean, percentage-wise, the 1, percentage-wise sounds like a chemistry lab. Anyway, percentage error measurement. But getting closer and closer and closer and closer and closer, eventually you become arbitrarily close, for all practical purposes close. So getting closer and closer and closer and closer until you're arbitrarily close and basically there. A single number L, well, if he's getting close to him, he must be a y value. And if x is getting close to him, well, what must these values be? X values. Okay, so right now, just from the paragraph, even if you didn't get much else, there's this whole closer, closer, closer until basically you're there idea. And then there's y's. Functions getting closer to y's, or no. Functions getting closer to a particular y, to a single number y. And then x getting particularly close to a single number a. But then if you guys take this paragraph and come down, hold on, is this something new? Is this something different? Or is this just a summary of that? The limit of f of x as x. Oh, they just put an arrow instead of approaches? A is L? Okay, that's a summary of that. And what's this? A summary of that. Because the limit means f of x is getting closer, closer. F of x is approaching L as x approaches A. And then what's this? The formula that, so all of this is encapsulated right there. The whole shebang. So when you see an LIM with an x arrow A underneath it and then an f of x equals L, what I mean is, oh, hey, you know what? The limit of f of x as x approaches A is L. The words are right up above. The verbal way of translating this statement are right up above. This is the notation. So here's the longer, and then here's the shorter, and here's the shorter, and here's the shortest way of summarizing, of notating this idea of, hey, as x approaches A, if f of x gets arbitrarily closer, closer, closer to a number L, is L. However, there's one idea that we haven't really touched on too much, and it's the idea of either side. We'll talk about that one more in just a second. You do not need to write these things down unless you really want to. But guys, didn't we in infinite geometric series talk about repeating decimals? We talk about how repeating decimals, it's an infinite sum. Can you possibly add an infinite number of values together? Like you personally, can you get all the infinite values and add them all together? No. But what can you say it equals? Ooh, a fraction. Isn't that 1/6? So even though you can't physically add an infinite number of numbers together, you can sometimes in things like repeating decimals and infinite sums of converging geometric series be like, oh, but I know who he is. He's 1/6. Got him. Give me a pizza. I'll show you 1/6. An infinite sum in a slice of pizza. But anyway, the infinite sum that you can't possibly do does have a limit, and so we identify him by his limit. MC Escher, the guy that I've talked about, I think back when we were talking about geometric series, the dude who painted all of these, well, actually, no. The copier printed them, and then I Mod Podged them onto painting canvases. But anyway, the guy who originally painted these that are up here on the wall, and one fell down, poor little guy, and then the Velcro wasn't sticking, so he hasn't gotten back up. That dandelion there kind of shows the idea of fractals. Fractals kind of have to do with triangle and Weihart and the whole infinite caravan thing. But these ones show infinite series in a sense, because you have bigger butterflies getting smaller and smaller and smaller and smaller and smaller and smaller, but theoretically going on forever. Same thing with this one. This one's a little bit different, but it's a similar idea. Then if I could find my other one, he's the best illustration of this. Nope, there's the ripple in the pond. Did I lose two? Why my poor ripple in the pond? Where'd my other one go? Well, that's okay. I can show you this one up here. I have another one that's similar to it, but he's not. He must have gone in that space. But do you guys see how you have a big old fish? What happens as you extend outwards? Okay. So my one arbitrary unit maybe got cut into maybe what, I don't know, like 2/3 and then like 2/3 and then like 2/3 and then 2/3 and then, oh, poor little guy, he keeps on. So what's happening? As the fishes get smaller, what happens to the number of fishes that are being fit in? More and more and more and more and more and more and more. How much can you divide something? Numerically speaking, forever. I can keep dividing and dividing and dividing and dividing, like 1/2, 1/4, 1/8, 1/16, 1/32. I can keep doing that forever mathematically, right? So if I can keep doing that forever, guess what's happening to the number of fishes? Dividing and dividing and dividing and dividing and dividing and dividing and dividing. The number of fishes is approaching infinity. If the number of fishes in a confined, limited space. And then, well, there's a whole other level of crazy. I don't know exactly if I should use the word limit having to do with fractals. But this guy and this mathematical concept that was developed, I don't know, I think mostly like in the 70s, maybe going into the 80s. Wait, 1970s, 1980s? No. Math was found thousands of years ago in places like China and Egypt and the Middle East and Africa and, well, all these different places simultaneously, which is kind of crazy because there was no communication way back then. However, with all of these different concepts, in the 1900s and the later 1900s, a fractal was talked about. But the guy said, wait a minute, fractal, I think he can be used for. And he basically is the foundation. This mathematical concept is the foundation for CGI and what it is today. What? CGI? It made them able to basically be realistic in computer animation. Oh, yeah, Star Wars being the key example. There's a really cool Nova, if you guys have ever heard of Nova, a Nova documentary on fractals. Super cool as far as medical imaging and with blood vessels and with CGI and all sorts of stuff. Math made an impact. Always has, always will. Just this is now something that, oh, I kind of care about that. Movies. Anyway, so maybe it wasn't all bad that you were talking about Endgame, just no other spoilers. Finding limits. Star Wars? Sure, we'll talk about Star Wars. Don't have as much investment in that one. Time or attention. Finding limits. Numerically, finding limits. If calculus is built on limits, we better figure out how to find them. Oh. Okay. Have just gotten this statement from the page before. And, wait a minute, where's the L? Well, that's the point. The answer. Remember how there's converge and diverge? Remember converging, there's an answer to the infinite sum, and diverging, there's not. Oh, I wonder if some limits exist and the some limits don't exist. Anybody? Mean Girls? The limit does not exist? Yeah. The calculus was real. Her problem-solving technique of just happening to see an answer on a board behind a cute boy's hair and be like, hey, it must be the answer, because what else could it be? Her process was a little bit flawed, but the math is real. Actually, HPrecalc AB kids wouldn't be able to solve that limit. She was in a first-year high school calculus class, and there was a little bit of flaw in there. But I feel like, what's Mean Girls? It's an experience. Maybe watch it, maybe not. Anyway, so we're trying to find the limit. And the first way to find limits, there are multiple ways, is using a table. Eventually, I want you to be able to see a limit and not even have to think about any of this. But the problem is when I have you do these shortcut rules of finding limits by like, oh, I'm just going to do this and be done. Yeah, it's cool. It's short. It's easy. A, it doesn't always work. And B, you have to have the idea of a limit down if it is so fundamental to calculus of what it is and what it's doing. As soon as you get to AP calculus, they're like, oh, you think you know it? We'll test you in a way that will trick you, and then you'll realize you don't fully know it as well as you did. Well, yeah, life kind of does that to you sometimes too. So here's the idea. If I'm trying to figure out what the limit is, let me show you where we go looking. Table, x and f of x, no big deal, right? It's like an xy table from Algebra 1. Table, x and f of x. Who's x supposed to be getting closer and closer to? A. And do you remember that in that paragraph I said from either side and said come back to it? What do you see on either side of A? Space. For what? Numbers. Oh, we have to go towards it from either side? Yeah. From either side. Now, I'm going to just quickly, because see I left space for like multiple numbers, right? I'm just going to put a little notation in here to show you A with a little negative in the exponent. I know it looks awkward. It's not A squared. It's not A cubed. It's not the square root of A to the 1/2. It's literally A from below. A from below. Numbers a little less than A in limit and limit notation. Just an idea. A from below. Numbers just a little bit less than A. Numbers just a little bit less than A. That's what's going to go on this side of A. And then guess what's going to go on that side of A? Numbers a little bit more than A. Numbers a little bit more, numbers a little bit less. I know it's weird. It's a new notation. We'll talk about it more in a couple pages. But if we're in a table, and if we're trying to get to A from below and from above, we're going to have to plug in numbers a little bit less than A and a little bit more than A. Now, whenever I say a little bit, that can be subjective, right? to 2? What's close and a little bit below? 1. 1.9 is a lot better. 1.99 is even better. 1.999. Not really close yet. Maybe. Numbers above 2. 10. Well, yeah. A little bit above 2. 3. Yeah. But when I say a little bit above, got it. Okay, so now, but wait, if we're approaching, maybe 2.01, 2.001, 2.001, 2.0000001. We're approaching and getting a little bit close. Numbers above, 2.1, 2.01, 2.001. Numbers below, 1.9, 1.99, 1.9999. What would we be approaching if those were our values? 2. As approaches, in this case, I'm giving the example of 2. We're looking to see what f of x is approaching. What f of x is approaching. So down here, as we're looking on this side, as we plug in those, aren't we going to have to plug in each of these to f, right? Plug in, and then plug in, and then plug in, and then plug in. As we plug in, let me show you some notation really quickly. The limit as x approaches a from below f of x is going to be or going to look like what we're doing here. We're going to see numbers, we're going to see numbers, we're going to see numbers, and hopefully we can see them getting closer and closer and closer to something. So for instance, if we were plugging in 1.9, 1.99, 1.999, and if we're getting out things like 3.5, 2.7, 2.667, 2.6666667, 2.6666667. Do you see how, like, there for a little bit, the 3.5 and the 2.7 and the 2.667, and then do you see how for a little bit there was some variation, but then soon it's going to get arbitrarily close to, I think, 2.6 repeating, right? But technically, when we look at this part of our table, we're only seeing the limit from below, or from numbers a little bit less. And as we come on this side, what were we doing? 2.1, 2.01, 2.001. We're going to see what's going on from above f of x. Once again, we'll go into this notation a little bit more. But as we look on this side of the table, we'll be like, hey, it's going here. And this side of the table will be like, hey, it's going here. And if they agree, if as you come towards x equals a from f is approaching whether from below or above the same single number L, then we are able to fill in that L and say, oh, hey, I'm going to actually make him a different color just so you guys realize that's not something that we just plug in and get out. It's actually something that we look at. So as we're coming from below and as we're coming from above, we're asking ourselves this big question, is there an L? Is there one number both sides agree on? Then we say, yay, the limit exists. And if there's not one number both sides agree on, we say the limit does not exist. So if I was to give you something as easy as this one. Hey, look, x is approaching 2. So we can start filling in our table of x and f of x and 2. And technically, we don't even really need to do it in red because we don't even need the function yet. We can just do a setup. And you guys just told me exactly what again, didn't you? Now, I won't make you go too much. To be safer than sorry, maybe we should go like 1.999999999. But for most well-behaved functions, we're going to talk about that a little bit later, probably tomorrow. Some functions are not very well-behaved, like kids. Anyway, it's okay. Some functions are really well-behaved except at one place. Also like kids. Anyway, some things bring out our worst sides, some things bring out our better sides. I've had a few chapels this year about putting yourself in a place where you will thrive and grow. Yeah, I know. Thanks, pop-ups. So guys, this so far is just me saying, hey, we should make a table and we should go towards 2. Do you see it? So far, we should make a table and we should go towards 2, from below and from above. You see it? I could label these guys as, oh, hey, their number's a little bit less than 2. could label those guys at numbers less than 2. Most people don't. You really just see it here. But I wanted you to know what this was. This just means numbers a little bit below. This just means numbers a little bit above. And not just a little, but a little, right? So what would this category be? Numbers a little bit above. So coming from below 2, coming from above 2, either side. What do we need to do, cool kids? Plug in, by hand. All right, get out your calculators just for a little bit. Calculators, let's go to our tables. Tables, but to get a table, don't you have to go to y equals first? All right, y equals, throw in 3x minus 2. Why should you change your mode? Why not just y1 equals 3x minus 2 and go to table? Isn't your table going to spit out like 0, 1, 2, 3, 4, 5, 6, 7, 8? Do we want it to spit out 1, 2, 3, 4, 5, 6, 7, 8? No, I want 1.9. I want 1.99. I want 1.999. Uh-oh. Well, if we want all of those, then don't we need to change our table setup? Oh, yeah, function mode. If you're in par or pole, that'd just be trouble. I agree with that. Good call. I didn't think about the mode. TI, what do we have? 84. Nope, I don't want that one. I want this one. Okay. So you guys should be in your y equals. You should have put your function 3x minus 2. That's our function, true? And then, if you haven't changed your mode yet to function mode, go ahead and do that. But can you guys do second window? You guys do second window? In table setup, isn't there something for the independent var where you can go from auto to ask? Go to ask. You want the calculator to ask you what x is. You're like, no, I'm in control. Take the control back from the calculator. Auto means it's just going to spit out whatever your settings tell it. But if you go second window, go down to independent and go ask instead, then your graphing calculator might have some things from earlier in the year because we reviewed this earlier. If you have numbers in there, can you just hit delete, 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 and then put in 1.9, put in 1.99, put in 1.999, put in 2.1, put in 2.01, put in 2.001. Double check in your groups really quickly that people know and see where to put in the function 3x minus 2. How to change the window to be ask instead of auto for the independent bar. And then I see multiple ones of you putting, oh, no calculator today, putting in 1.9, 1.99, 1.999. Uh-oh, where's your y1? Oh, you need to put them in first. So put in your function. And then now we'll start plugging into what you... Oh. Why doesn't it like you? Let's try again. Maybe it just didn't like it because it wasn't there. What? Oh, that's weird. Oh. Oh. Here, check it. 1.99. You want it to be asking you for x's, but you said ask for y's, and so it doesn't show you until you click on it. I would do auto, like after you give the x, it's like, no, just give me the y. There you go, now try. All right, you guys getting numbers, right? Okay, hopefully you guys saw from coming from below 3.7, 3.97, and 3.997. What would you think would be the answer then to the limit as x goes to 2 from below of f of x? You think? Did anybody keep going and be like, I wonder what 1.999 is going to be? Does it? Pause. Can you take your cursor and go up? Was it really 2 or did it run out of decimal places? Whoa, it's really 1.9999999. Now, hold on. Was it really 4? Go over. Was it really 4? Or was it 3.9? There's only so many digits, so it's going to round eventually because it became, for the calculator, arbitrarily close. Because the calculator says, I only care in my table, or at least my programmers only gave me space for 4 decimals? 5 decimals? Anybody figure that out? Or 5 numbers? 4 or 5 numbers? 5 numbers. 3.9. Anyway, what's it look to be approaching? Looks to be approaching 4 from below. But hopefully in your table you didn't just come from below, because what does the informal definition of a limit say you need? Either side. Well, yeah, both sides. I'll take it. Oh, either. Ooh. Someone asked for prayer for their aunt today. I was like, ooh. Either aunts. We're being very formal. What do you guys see? 4.3? 4.03? I have some friends who, or I should say, there's like a group of them, but a friend that married a guy from Jamaica, and they talk about their aunties. I'm like, oh, they're so cute. Did they say auntie? Anybody in here say auntie instead of auntie? Auntie? Or aunt? Aunt. You guys are awesome. I'm just the good old-fashioned American South. Aunt. Aunt. Hey, what's going on from above? What's going on from above?
We're getting closer to 4.
You guys are so good at this. Look! Whoa! You're getting closer to 4. You're approaching 4, which means the limit seems to be 4. So wait a minute. If these two agree, what did I say you're allowed to do? Put in, well, hold on. Here's the... Can I put in 4? Yes. This time. This time. What? But here's the long story short. The long story short is, what's the answer to the limit as x approaches 2 of f of x? 4. Oh. But here's the crazy thing. I know back here and up here in the table, I put the L. And sometimes this is true. We are looking from both sides, and if they agree, we can make the final answer. But the struggle is, guys, this L does not always go in this spot. Oh, I just attached it. Now I don't know how to get it out. I was going to erase it. That's okay. We'll keep going. Get rid of this. Boop, boop. So go for this one, guys. Ready, set, approach. Ooh. Go gadget approacher. No one knows Inspector Gadget anymore. It's so sad. Tune or the movie? Or both? Movie? Yeah. There's like an old movie and a newer one. The newer one is fun. Then there's like the cartoon from a long time ago. There it is. It's like a classic from even before I was a kid. It's my older sister who watched Inspector Gadget, the cartoon. Well, we didn't have cable. I'm sure there were reruns forever, but... Animaniacs, that was my childhood. Pinky and the Brain. TV does teach you stuff. Okay, I'm going to double check you guys know what you're doing, but I'm hearing a lot of good work, so I think you have the idea down. Because I'm really hoping you guys are going to -3. Here's a question, though. Did you put the right numbers on the right side? Did you do -3.1, -3.01, -3.001? Remember, negatives and positives work differently on number lines. If I'm going to -3, it's different than 3. Below 3 is like 2.9, 2.99, 2.999. Below -3 is -3.1, -3.01, -3.001, right? Because you're more negative. You're farther from 0 on the left of numbers, but you're closer to 0 on the left of positive numbers. Just got to be careful. Be on the other side of -3. See it? Your brain gets a little confused on these ones. Oh, 3. Your calculator would say 3 because it would start rounding pretty soon, but Did you change your y1? Ooh, there's a fraction now. Huh. What's up?
I put in -3.
You weren't supposed to put in -3, cheater. Aren't you supposed to be approaching? But you're bringing up exactly what I'm going to be talking about in just 1 second. Keep quiet, but be ready to answer when I say what happens. Uh-oh, I plugged in -3.004. Did you guys get -0.1639 and -0.1664 and -0.1666? Did anybody just get curious and do -3.0000001? -0.1167. Nope. Scroll up and look at it. Scroll up and look at it. It's -1.666666666666666. Is that a fraction? Hey, that's a repeating decimal. We just saw it, didn't we? Look at me trying to be helpful. Whoop, whoop, whoop. What decimal is that? So, from below, I know it's awkward, a -3 negative, but you're entirely right. Below sure looks like -1/6. From above, did you guys keep going and check out from above if it matches something different? -2.9, -2.99, -2.999. Man, I sure see -0.1695. I sure see -0.1669. I sure see -0.1666. Oh my, well, 7, but if you go look at it, isn't it 66666? What's it look like from above, cool kids? So what can I say is the limit? They agree. No, the limit agrees, right? Do they agree from either side? The approach. Guess what? The answer to the limit is -1/6. But Kyle, what happened when you plugged in -3? So question, is the limit always here? What was different? What was wrong? We'll have to talk about that tomorrow. Bye, guys. Toodles. Do not do all of homework because we've only looked at the idea. We haven't looked at the shortcut. You're sure going to want to see the shortcut tomorrow.
Is there a way to make
Bye.
the table decimals instead of fractions?
Yeah.
I don't know how it.
It's probably because of that. Oh, stinkers is the newer calculator.